Welcome to our exploration of the power of DC series motors. DC series motors are a type of electric motor where the field windings are connected in series with the armature windings. This series connection is what gives the motor its unique characteristics. When a DC voltage is applied, the current flows through both the field windings and the armature windings, creating a strong magnetic field. This strong magnetic field interacts with the current flowing through the armature to produce a powerful torque, making DC series motors ideal for applications that require high starting torque. Imagine a crane lifting a massive shipping container. The initial torque required is immense. This is where DC series motors shine, providing the muscle to get the load moving. One of the key advantages of DC series motors is their ability to generate high torque at low speeds. This makes them well suited for applications where heavy loads need to be moved, such as in cranes, hoists, and electric trains. DC series motors are also known for their excellent speed control characteristics. By varying the voltage applied to the motor, the speed can be adjusted over a wide range. This is crucial in applications like electric vehicles, where precise speed control is essential for smooth acceleration and deceleration. Furthermore, DC series motors are relatively simple in construction and cost-effective to manufacture, adding to their appeal in various industrial and consumer applications. In contrast to other DC motor types, series motors can be easily reversed. This is achieved by simply reversing the polarity of the applied voltage, causing the current to flow in the opposite direction through both the field and armature windings. This reversal of current direction effectively flips the magnetic field, leading to a change in the direction of rotation. This reversibility is a valuable feature in applications where bidirectional operation is required, such as in electric vehicles and winches. Let's delve into the current's journey, powering the motor. The journey of current through a DC series motor begins at the power source, which provides a direct current, DC, voltage. This DC voltage is applied across the motor terminals, and due to the series connection, the current follows a single path. It first flows through the field windings, which are coils of wire wrapped around the motor's stator. These windings are designed to create a strong magnetic field. As the current passes through the field windings, it magnetizes the stator poles, creating north and south poles. The strength of this magnetic field is directly proportional to the amount of current flowing through the windings. Since the field windings are in series with the armature, the magnetic field strength also varies with the load on the motor. From the field windings, the current continues its journey into the armature windings, which are wound on the rotor. The armature is the rotating part of the motor, and it's free to spin within the stator's magnetic field. The armature windings are arranged in a specific configuration, typically a closed loop, to interact effectively with the magnetic field. As the current flows through the armature windings, it generates its own magnetic field. This magnetic field interacts with the stator's magnetic field, resulting in a force that acts on the armature. The interaction of these magnetic fields is governed by the principles of electromagnetism, which dictate that like poles repel and opposite poles attract. Now let's explore magnetic fields and torque. The driving force. The interaction of the magnetic fields from the stator and the armature is what generates torque, the rotational force that drives the motor. The stator's magnetic field tries to align the armature's magnetic field, and this interaction creates a twisting force on the armature. This torque is proportional to the strength of both magnetic fields and the angle between them. In a DC series motor, the torque is directly proportional to the square of the armature current. This is because the current flowing through both the field windings and the armature windings is the same. As the load on the motor increases, the armature current also increases, resulting in a stronger magnetic field in both the stator and the armature. This increase in current and magnetic field strength produces a higher torque, enabling the motor to handle the increased load. This characteristic makes DC series motors particularly well suited for applications requiring high starting torque, such as cranes and hoists. When a crane starts to lift a heavy load, the motor needs to overcome the inertia of the load and generate enough torque to get it moving. The direction of the torque depends on the direction of the current flow and the orientation of the magnetic fields. By changing the direction of the current through either the field windings or the armature windings, the direction of the torque can be reversed. This is how the direction of rotation of a DC series motor can be controlled, making it suitable for applications requiring reversibility. Section 4. Armature rotation. Setting things in motion. The torque generated by the interacting magnetic fields acts on the armature, causing it to rotate. The armature is mounted on bearings, allowing it to spin freely within the stator. As the armature rotates, the armature windings continuously cut through the stator's magnetic field, inducing a voltage across the armature windings. This induced voltage is known as back EMF, or electromotive force, and it opposes the applied voltage. The back EMF is proportional to the speed of the armature rotation. The faster the armature spins, the higher the back EMF generated. The back EMF plays a crucial role in regulating the motor's speed. As the armature rotates, the commutator, a segmented ring on the armature shaft, comes into contact with the brushes. The brushes are stationary contacts that provide the electrical connection between the armature windings and the external circuit. The commutator and brushes work together to reverse the direction of the current flowing through the armature windings every half turn. This reversal of current is essential for maintaining continuous rotation. Without it, the armature would simply oscillate back and forth as the magnetic fields tried to align. The commutator ensures that the current flow is always in the right direction to produce torque in the desired direction of rotation. Section 5. Back EMF, the speed regulator. Back EMF acts as a natural speed regulator in a DC series motor. As the motor speeds up, the back EMF increases, reducing the effective voltage across the armature windings. This, in turn, reduces the armature current and the torque produced by the motor. As the motor's load decreases, it tends to speed up. However, this increase in speed also increases the back EMF, which counteracts the speed increase. Conversely, when the motor's load increases, it tends to slow down. This decrease in speed reduces the back EMF, allowing more current to flow through the armature windings. The increased current results in higher torque, enabling the motor to handle the increased load. This self-regulating mechanism helps to maintain a balance between speed and torque, ensuring that the motor operates within a safe and efficient range. In summary, the DC series motor, with its unique characteristics, plays a vital role in various applications. Its high starting torque makes it ideal for heavy-duty applications such as cranes, hoists, and electric trains, while its speed control capabilities make it suitable for electric vehicles and other applications requiring variable speed operation. The interplay of magnetic fields, current flow, and back EMF ensures efficient and reliable operation, making the DC series motor a workhorse in the world of electric motors.